I'm Mark Arenes, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 30. The problem tells us that there are only three numbers which are equal to the sum of the fourth powers of their digits, excluding the special case of 1, which is always the sum of any powers of its own digits. The problem then asks us to find all numbers, again excluding 1, which are the sum of the fifth power of their digits. The solution is the sum of all such numbers. Before we start coding, let's convince ourselves that the set of numbers we're looking for is actually finite. In fact, we're going to do one better and get an explicit upper bound. If we restrict ourselves to one-digit numbers, then the largest possible sum of fifth powers is 9 to the fifth, or 59,049. Nothing really learned so far. If we restrict ourselves to at most two digits, then the largest sum is 9 to the fifth times 2, representing the sum of fifth powers of the number 99. This is 59,049 times 2. For three-digit numbers, the pattern continues, and our upper limit on sums is 59,049 times 3. In general, if we allow a maximum of n digits in our input, the upper bound on the sum of fifth powers of digits is 59,049 times n. Let me put that another way. If our input is strictly less than 10 to the nth power, then our output is strictly less than 59,049 times n. As the input grows exponentially, the output grows linearly. Equivalently, as the input grows linearly, the output grows logarithmically. That is, our function's growth rate is big O of log n. The important thing here is that the input grows much faster than the output, and we're looking for fixed points. That is, we're looking for inputs for whom the sum of fifth powers of digits is equal to the original value. At some point, the outputs won't grow fast enough to keep up, and we can actually find that point. Consider inputs containing up to 5 digits. The largest possible sum of fifth powers for a number with at most 5 digits is 59,049 times 5, or 295,245. No problems yet. For 6 digits, the largest possible sum is 354,294. So it follows that any 6-digit number greater than 354,294 cannot possibly be equal to its own sum of fifth powers. Further, for 7 digits, the maximum possible sum is 413,343. Note that this sum is a 6-digit number. So once we're looking at 7-digit numbers, there's no way our input can be equal to its sum of powers, and the sum of powers will never catch up again. This means that the largest possible fixed point for this sum of powers function is 354,294. Aside from that, this is a simple brute force problem, and it'll go very similarly to the last challenge. We're going to write up a draft in Raku, then we'll shrink it down to one line just for a bit of fun, and finally we'll introduce a stack-based esoteric language reasonably similar to Seriously. If you followed the last video, this one should be no trouble at all. First, let's write a nice simple imperative solution in Raku. We'll start with a sum of powers function. This function takes two arguments, the input number and the power to raise each digit to, and it functions as a simple loop until the input number's digits are exhausted. We've used the isCopy trait before, but we'll recap quickly. In Raku, by default, arguments are passed using whatever calling convention the interpreter pleases, and we're not allowed to modify those arguments. If we want to modify the arguments, we have to specify what we want to happen. The isCopy trait tells Raku that we want the variable called n to be a shallow copy, unrelated to the original value passed in. On the other hand, we could have written isRW, short for isReadWrite, which would force callers to pass a writable container, the equivalent of an L value in C++, and any modifications to that writable container's value would be visible to the caller. Aside from that, the rest of the program is pretty straightforward. Loop from 2 up to our established limit of 354,294, add together any values which are the sum of their own fifth powers, and print the total. This runs in about 2 seconds and produces a correct answer. That's great, but if you saw our last video, you know what's coming next. This is an 18-line program, which is simply a travesty to Raku and its history in Perl. We can shorten the whole thing down to one line like so. There are a few things going on here. First, Raku's filter function is called grep, after the Linux command line utility of the same name, and it's actually a sort of all-in-one filter and grep function. Specifically, the grep function doesn't just accept a callable object. It accepts any object which supports smart matching. Raku's smart matching is a lot like the Ruby triple equals operator, except that in Raku, it's called excepts written in all caps. In Raku, any type object, such as int or bool, can be used as the subject of a smart match and it will perform a type check. Strings and numbers check for simple equality, regular expressions, naturally, match the string or string-like argument, and callables get called. Finally, similar to Ruby, if no other case applies, the fallback is to compare for strict object identity. In our case, we pass a block of code which is a type of callable, so it gets called. The sole argument to the callable is named n. Inside the block, there are a few clever tricks. Like Tickle and Lua, Raku likes to treat strings and numbers in a uniform way. However, unlike Tickle and most shell languages, Raku actually does give us distinct types for strings and numbers. The trick is that both strings and numbers inherit from the common parent class cool. Raku's official documentation says that the name cool stands for Convenient Object-Oriented Loop, But let's be honest here, they called the class cool because what it does is kinda cool. Specifically, any methods you might normally define on the string or numeric classes are defined on cool and coerce their arguments. So even though the n variable is a number in this example, we can call the string method split on it, and we get the nice Lua-like coercion for free. Once we have the digits, we raise each one to the power of 5 and sum. We could have written this map call using the same block syntax as before, but for short blocks, Raku lets us use the star character as a placeholder for arguments. So this is a callable code object which raises its single argument to the 5th power. In case you're wondering, aside from the Raku parser supporting a single star either as an infix operator or as a standalone value in its own right, the syntax we used here is not special cased. A star, when used as a single value, is actually a special constant whose type is, and I promise you this is true, whatever. No, I don't mean that its type is whatever you want, I literally mean there's a class in Raku called whatever, and that's the class we're dealing with here. Most operators in Raku are overloaded to work on the object of type whatever, and will return, wait for it, an instance of the whatever code class, which is a callable object. For those of you old enough to remember C++ before we had proper lambdas, you can think of Raku's whatever infrastructure as being very similar to the C++ library boost.lambda. But alas, we're getting off track. This too gives us a correct answer rather quickly, and that's really all we need to do today. As promised, we'll be working in another stack-based isolang a lot like Seriously, CJam, and GolfScript. This week, we'll be working in Stuck. Stuck is a stack-based esoteric programming language written in Python. It's actually written in Python 2, and while I probably could have found a Python 2 interpreter lying around somewhere, the 2-3 utility provided by Python did a great job of modernizing the code where needed. So I'll be running a slightly modified interpreter in Python 3. There's a few other things of note about this interpreter right off the bat. The Stuck interpreter is split into a core package called stuck.py, which manages the execution environment, and two plugins called stuckbase and stuckmath. These plugins implement most of the built-in functions used in Stuck code, so I'll assume we're using them today and won't mention them again. But because of the way the Stuck interpreter dynamically loads modules, you must be running the interpreter from its own working directory. If you try to invoke the interpreter from any other folder, it'll run your code, but none of the standard built-in functions will be available. There's one other thing I'd like to note for those of you brave enough to follow along at home. If you find yourself writing Stuck code and you get stuck, you can enable debug mode with the -d compilation option. No, you don't pass -d on the command line, you put it at the end of your source file. That is, if you want to enable debug mode, make sure the final two characters in your source program are a hyphen followed by a lowercase d. You'll also need to make sure your code editor of choice isn't automatically inserting new lines into your files. In Emacs, you can do that by switching to fundamental mode rather than text mode, which is what I often use for these esoteric programming languages. With all of that in mind, let's start talking about the language itself. Stuck has no equivalent of the backtick from Seriously, which pushed function literals onto the stack. When we want to represent a function, or even just a block of code for a loop, we're just going to use the string data type. String literals are enclosed in quotation marks, which can present a problem we'll see several times in Euler's melting pot going forward. Since the starting and ending delimiters are the same for blocks of code in Stuck, it becomes difficult to nest blocks of code in order to have loops within loops, or even loops inside of functions. In the particular case of the Stuck programming language, we have a partial solution. Stuck doesn't have normal C-style escape sequences with backslashes, but a pair of adjacent single quotes in a string literal will be treated as a double quote. In this way, we can nest ourselves one layer deep in strings using a pair of single quotes, but we can't go deeper without some rather obnoxious string substitution tricks. Fortunately, for today's challenge, we won't need to go more than one layer deep. Aside from that, we've seen a lot of this before. Plus, minus, star, and forward slash are our four basic arithmetic operators. All of them operate on the main value stack, popping two values and pushing their result. Stuck supports floating point arithmetic, so the quotient of two numbers can be a non-integer value. We also have %sign for modulo and caret for exponentiation, which will be very handy in a challenge centered around raising numbers to the 5th power. We can easily generate lists using lowercase and capital R, each of which pops a single integer off the stack and produces a list of numbers up to that value. Lowercase r starts at 0 and goes up to but excluding its upper bound, while uppercase r starts at 1 and includes its upper bound. Our main looping construct, and the only one we'll need today, is the colon command. The colon command starts off by popping a single value off the stack, which will be our loop body as a string. Then the command can do one of two things, depending on whether the next value on the stack is a list or not. In the simpler case, the next value on the stack is not a list. In this case, the loop body is executed once for each element on the stack. During execution of the loop body, the usual stack is replaced with a temporary virtual stack containing only the element we're currently operating on. At the end, the bottom values of each of the virtual stacks are combined together to form a new value stack. For example, consider this program. First, we push some numerical constants, 1, 2, and 3, onto the stack. Next, we push a string literal consisting of our loop body, in this case, the string containing 1 and plus. Finally, we run the loop with the colon command. This will have the net effect of adding 1 to every element of the stack. But let's zoom in a bit to see exactly what's happening. At the point in our program when we run the colon command, there are 4 elements on the stack, 3 numbers and a string. We pop the string and store it for later. Then we look at the next value. The next value is the integer 3, which is not a list, so we're in the simple looping case. We're going to run the block 1+ for each element on the main stack. We create a virtual stack consisting of the number 1 and run the block, which produces the number 2. Our main stack at the end of loop execution will start with the number 2. Next, we take the second stack element of 2 and make a new virtual stack for it. After running the block, the virtual stack consists of the number 3. Finally, we take our last value off the main stack, which is 3, and run the block to get the number 4. After the colon command finishes executing, our main stack consists of 2, 3, and 4. At the end of execution in a stuck program, as long as we don't use any explicit printing primitives, the stack is automatically printed to the screen. So the numbers 2, 3, 4 will be printed at the end. All of this was predicated on the second stack element, the one immediately under our loop body, not being a list. If the second stack element is a list, then we instead pop that value and use it for iteration, pushing a list of the results. Here, we use the range primitive to generate the numbers from 1 to 10 inclusive. Note that we haven't generated 10 stack elements, merely one stack element which happens to be a list. Then, as before, we push our loop body as a string. Our loop body will multiply its element by 2. Next, we run the colon command, starting our loop. Since the second stack element is a list in this case, we pop that list and run the loop body for each element, pushing the resulting list back onto the main stack. At the end of program execution, the only value on the stack will be a single list of the numbers 2, 4, 6, 8, 10, and so on up to 20. That list is implicitly printed out by the interpreter using the Python syntax for lists. With that in mind, the actual code we need to write consists only of basic control flow, so we're actually ready to get started. As a reminder, this was our Raku code to find the answer. Well, this was the original solution, not the offensively short solution we came up with next, but this is much easier to translate into a stack-based language. The first thing we'll do is generate the range of numbers from 1 up to 354,294, our known upper bound we established earlier. Then we'll loop over those values to produce a list. In Raku, we used a filter function to remove certain list elements. Stuck actually does have a filter function, but its block argument is literal Python code, and dipping into literal Python to solve this problem felt a little like cheating to me, since we're supposed to be solving this in Stuck. So instead, we'll use the for each command. Inside the loop body, we start with an element of our input range. What I want to end up with is either the original element, if it should be included in our sum, or 0 if not. Since 0 is the additive identity, zeros in our resulting list won't affect the ending sum. The first thing we're going to do is duplicate the top of the stack, 3 times. That's right, I want 4 copies of our input number onto the stack. The duplicate command is the underscore, and we need 3 underscores to get the job done. You may be wondering why I need 4 copies, but I promise we'll put each of them to good use by the end. Now, in our Raku program, we had a loop on the inside that summed the digits. I already mentioned that Stuck can nest strings 1 layer deep by encoding double quotes as pairs of single quotes next to each other, so we could do that for our Stuck program as well, but I'm actually going to do something far simpler. Thanks to our explicit upper bound, every number we're going to be working with consists of at most 6 digits. So I'm going to take a digit and raise it to the 5th power 6 times, since that will definitely be enough to handle any of our input values. To that end, let's get the last digit of the top input value and raise it to the 5th power. Then we'll use the semicolon command to swap the top 2 stack elements. We've already seen the final digit of our input number, so let's divide it by 10 to get rid of that digit. I told you division is floating point in Stuck, and we want a truncated integer, so we use the close parenthesis command to floor the result. Finally, duplicate the top of the stack. Now comes the fun part, or the extremely boring part, depending on who you ask. Forget about the bottom 2 stack elements for a moment. When we started this, the top 2 values on the stack were our input number twice. And now, the top 2 values on the stack are the input number, just without the final digit. If I copy-pasted the code we just ran and put it in the loop body a second time, it would do the same thing again, producing another digit raised to the 5th power on the stack. And that's exactly what we're going to do. Now we've dealt with 2 digits. Do it again, and again, and again, for a total of 6 times. That deals with all 6 digits. On our final run, we won't duplicate the top of the stack again, since we don't need the iterated number anymore. In fact, we'll pop and discard the top of the stack with the lowercase y command. One minor point that's worth mentioning here is what happens if we have a number with fewer than 6 digits. In that case, once we've simply run out of digits, the iterated value on the top of the stack is simply 0. 0 mod 10 and 0 divided by 10 are both 0, so the remaining iterations will simply push zeros onto the stack, which, as already mentioned, won't affect a summation calculation. Now we have 6 digits on top of the stack. Sum them. Then use the equal sign command to compare for equality against the original input value. That's the 3rd copy of the input value we've used. Finally, multiply the comparison result with the final copy of the original input value. I promised you we would use all 4 copies of the number. You may wonder what it means to multiply a boolean with an integer. Stuck really just falls back to Python semantics for most things. Python does have a distinct boolean type, but it's actually a subtype of int, with false acting like the number 0 and true acting like the number 1. So if our boolean is true, we multiply the input value by 1, effectively leaving it unchanged. If our boolean is false, we multiply the input value by 0, which will guarantee our result is 0 in that case. This is exactly the behavior we want. Outside our loop, we have a list of numbers, many of which are 0, and we want to sum that list. We could write another loop to do it, but Stuck actually has a built-in command for summations, the Greek capital letter sigma. Like the colon for each loop, the summation command is overloaded based on whether the top stack element is a list. If it is, we sum that list. If not, we sum the whole stack. In our case, we have a list on the top of the stack, so we produce the sum. Finally, subtract 1 from the final sum, since we included the number 1, which is trivially a sum of its own digit powers, and the problem explicitly told us to exclude it. Since we never printed anything at any point during our program, Stuck implicitly prints the stack, which consists of one value, the solution to our problem. This program runs instantaneously and solves Project Euler problem number 30 in Stuck. Tune in next time when we solve Project Euler problem number 31 in our first ML dialect, Standard ML. See you guys then. If you find yourself writing Stuck code and you get stuck, God damn it.